I now call to order the Society's 2,403rd meeting in the 148th year since its founding in 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Raman Sundrum in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements, a reading of the minutes of the 2,402nd meeting and the lecture on wearable biosensors by Todd Coleman. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. But first, please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. Also, please join me in thanking the sponsor of tonight's lecture, PSW member Frank Robert. Frank is a space practice lead at A.T. Kearney and is involved with Australian efforts to develop an Australian space agency. He is one of PSW's live stream viewers when he's traveling or at home in Australia, and he may be watching tonight's proceedings. And if so, hello, Frank, and thank you. I am pleased to announce that the following new members have been elected to the Society. Sonia Killey, a broker interested in neurosciences and physics, who comes to PSW through PSW member Tim Thomas and other friends at the Cosmos Club. Seth Morris, an engineer with MITRE, interested in space and telecommunications, the Internet of Things, and bioengineering, who has come to PSW through attending PSW meetings. And Charles Huttner, Executive Director, retired, of the Aerospace States Association, interested in aerospace engineering, physics, especially quantum mechanics, astronomy, and cosmology, who comes to PSW through PSW member and colleague Tobin Koziahar. And tonight's speaker, Raman Sundrum, whose background and some of whose interests will be clear to you from tonight's lecture. Please join me in welcoming them to the Society. There is a signed volume of the reprint of Volume 1 of the PSW Bulletin for all new members. If you're a new member and you have not yet received your copy of Volume 1, please see me after the lecture to pick it up. Why would you be interested? Because it will tell you why it was called the Philosophical Society of Washington, and also lists all the original members. And it also tells you how to calculate pi to 30 decimals. Also, we'd like to welcome members of the Washington Area Astronomy Meetup Group. How many of you are from that group? Raise your hands for a minute. Okay, a few of you are from that group. Well, welcome. We also invite you to join the PSW meetup group as well, and to join PSW. Recording Secretary James Heelan will now read the minutes of the 2,402nd meeting and the lecture by Todd Coleman on wearable electronics delivered here at the Cosmos Club on January 25th, 2019. James.
Hi, good evening. I think it was January 15th.
What did I say?
25th.
Sorry.
On January 15th, 2019.
Actually, I think it was the 25th.
January 25th, 2019, President Larry Milstein called the 2,402nd meeting of the Society to order at 8:02 p.m. here in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Todd Coleman, Professor of Bioengineering and Director of the Neural Interaction Laboratory at the University of California at San Diego. His lecture was titled, Wearable Biosensors. Coleman said his work lies at the intersection of analytics, neuroscience, and technology development. His team develops devices that sense biological activity with high accuracy and minimal disruption. In 2011, Coleman worked with doctors and nurses from the UCSD Neonatal Intensive Care Unit. He learned they needed to constantly monitor infants' body temperatures, but that doing so was stressful to the infant and disruptive to the infant-mother bonding. Coleman's team addressed that problem by creating a temperature sensor that adheres to an infant's skin and could be wirelessly read without disturbing the infant. Coleman's team later adapted that technology to create ECG and EEG sensors. Coleman then addressed the engineering challenges of developing epidermal electronics for wireless patient monitoring. He described how his team resolved issues of RF tuning, mass production, biocompatible substrates, low power, small components, and clinical grade accuracy. More recently, Coleman has worked to create sensors to monitor electrical activity in the human digestive system to diagnose gastroenterological problems, an idea developed and discarded as unfruitful in the 1980s. Coleman reviewed that early research, developed some gastroenterology, and concluded that his team could engineer away the limitations of the early studies. Coleman's techniques proved accurate to the measures of invasive procedures currently used to diagnose certain problems. Coleman's team has since developed a wearable EGG system for 24-hour ambulatory monitoring. This technology will allow doctors to identify problems that do not necessarily correlate to symptom severity and that do not present themselves during the time-limited window of a patient's appointment. Coleman sees near endless opportunity for wearable biosensors. He is currently exploring applications for monitoring sleep, stress, GI function, behavior, diet, and environment. After a robust question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the Society. At 9:39 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 1 degree C. Weather, clear. Attendance in the Powell Auditorium, 96. And viewing through the live stream on the PSW Science YouTube channel, 18. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Thank you, James. Are there any corrections or comments to the minutes? If none, I will entertain a motion from a PSW member to accept the minutes as read. Do I have a second? All members in favor, say aye. All members opposed, say nay. Okay, the minutes are accepted as read and will be posted without alteration to the website in due course. We now turn to tonight's lecture on differentiation in the embryonic universe. And it is my pleasure to introduce tonight's speaker, Raman Sundrum. Raman is John S. Toll Chair and Distinguished University Professor of Physics at the University of Maryland, College Park, and he is the Director of the Maryland Center for Fundamental Physics. He was previously Alumni Centennial Chair of Physics and Astronomy at the Johns Hopkins University. Raman is interested in the fundamental forces of nature and their connections to theoretical extensions of relativistic space-time, including supersymmetry and extra dimensions, and in novel mechanisms at the intersection of relativity and quantum mechanics. His research provides theoretical foundations for empirical experiments ranging from searches for new particles at the LHC to precision cosmological observations. He is particularly interested in the physics of the very early universe, as you will hear tonight. He is an author on over 70 scientific papers and speaks on his work widely to both professional and general audiences, including appearances on BBC television. Among other honors and awards, Raman is a fellow of the American Physical Society and the American Association for the Advancement of Science. He was distinguished visiting chair at the Primeval Institute and was a Moore Fellow at Caltech. He is the co-recipient of APS's Sikorio Prize for Theoretical Particle Physics with Lisa Randall of Harvard for their development of the Raman Sundrum theoretical models of higher dimensional space-time. Raman earned a BSc in mathematics at the University of Sydney in Australia and a PhD in theoretical particle physics at Yale. He also did postdoctoral research at Berkeley, Harvard, BU, and Stanford. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Raman to the podium.
Testing the mic. It's okay.
I think you need a little bit more volume.
Okay. Thank you. I got this. Okay. It's great to be here. So I think this title, I hope you understand by the end of the talk, but basically the universe, like other organisms. So in biology, in developmental biology, then when you have an embryo, of course, there are two challenges that face the embryo. One is to grow and multiply its cells, but also there's the challenge of the cells having to differentiate themselves and take on specialized activities, given that they have the same genetic code. Okay, so there's a sort of similar set of challenges for the early universe, and that's what this talk is about. Okay. This is sort of the subtitle, which is basically to find out how the early universe does these things. We need to read the fossil records, which are, very roughly around the time of the Big Bang. And the subject will have sort of two specializations. It's at the intersection of cosmology, which is the study of the evolution of the universe, and particle physics, which for the purpose of this talk, you can think of as like the microscopic DNA of the universe. I tend to come at it from this direction. This is my day job here, and I'm sort of a plodding student from the cosmology point of view. So I'm going to be telling you the story of the entire universe, so I have to be very selective in what I say, and so I will pick and choose in some idiosyncratic way, which may be sort of criminal from the point of view of a professional cosmologist, but is sort of tilted towards my particle physics taste. Okay, so since this is a philosophical society, I wanted to start with a philosophical question. Why are we here? Okay, as opposed to over here. Okay, so now what do I mean by this? I mean, if we look at this picture from the Hubble Space Telescope, why do we find ourselves in, we are in this galaxy, and here is a perfectly good patch of empty space. And so there's some differentiation going on in the universe right there. In fact, from a very fundamental viewpoint, we should ask this question. The laws of nature, if they're worth calling laws, if they're fundamental laws, are the same everywhere. So how does nature decide where to build a clump of galaxies over here and not over here? Who makes that call? Okay, so that's one of the puzzles we're going to tackle. Now, we are greatly aided by Newton's inverse square law of gravitation, which says that if you have a even roughly uniform distribution of matter, so everywhere looks roughly like everywhere else, but if it's a little bit denser in one region, then Newtonian gravity starts making that, it accentuates that little overdense region. And if you have a region which is a little less dense than average, it dilutes even more, okay? So we can see this in, by basically running a universe inside a computer where we run Newton's laws, not me, but astrophysicists who can actually put this on a supercomputer. But what they're doing is they're putting many, many masses inside a patch of a model universe. And the thing that we're keeping our eye on is the effect of Newtonian attraction. Now, there are other effects that are put into there that make it very realistic, but the thing that's going to catch your eye is the power of Newtonian attraction to create structures from something that looks more or less uniform inside this box. So that turns out to be a very challenging thing, to take each one of these little particles or masses and allow each of them to attract the other according to the inverse square law, and to keep the collective effects and plot this in time. Now, to do this, I need to turn on this other thing right here and go here. Okay, so you can see here the effect of Newtonian gravity, and I'll run it one more time just to say, you start with something very uniform. So this thing called z is just an astrophysical measure of time, where the smaller z is closer to now. But let's just run it again to see how the uniformities slowly lead to a highly structured space in which clusters of galaxies, which is what your eye would be seeing here, whole clusters of galaxies start to form, but starting from a very, very uniform initial state. Okay, let's turn back to the show here. Okay. So we can compare the results of, so here's just a few frames of that. We can compare the results of doing this kind of a simulation where you start from something very uniform to what the universe actually looks like. So I should say that most of the mass in the universe, which is what's being plugged into this simulation, most of the mass in the universe comes in the form of dark matter, which is a kind of matter which is not made out of the usual protons, neutrons, electrons that the rest of us are made out of, or even most of the visible galaxies are made out of. But they're just being colored in blue here so you can see them. So this is most of the mass of the universe is going through this kind of an evolution in the simulation. And we can compare that with what the universe actually looks like here. So here is a survey of the universe going very deep. It's on a very, very large scale. And you see the same kind of filamentary structure that we see in the simulation, telling us that roughly the simulation and the effects of Newton's laws are roughly capturing what we see today in the sky. Given that I told you that dark matter is not made out of the usual stuff, and it's called dark matter because you can't see it, you may wonder how we are actually getting something from a simulation of dark matter that looks like a survey of galaxies in the universe. And that's because the visible galaxies, in a sense, they sort of track the dark matter distributions. They are like a kind of glowing pin, that's stuck on the otherwise dark matter. So by looking at the visible galaxies in this survey of the entire universe, we are getting a sense of where the dark matter is hidden. And we can see from these kind of surveys that they are roughly tracking the behavior that we see in these simulations under the effects of Newton's laws. Okay, so we have the sense of what is going on in terms of forming this highly structured universe that we live in today. Okay, very good. Of course, Newton's law was not the last word on the subject. The truth theory of gravity, as best we understand it, is general relativity. And it comes by this insight of Einstein's that whatever should replace Newton's law, or Newton's law acts instantaneously. If you believe Newton's law, it acts instantaneously across large distances. And yet, in the 19th century, the emergence of electromagnetism showed that in fact, light is the fastest possible speed, and it's finite, which is inconsistent with the ability of Newton's laws to act instantaneously. So Einstein faced the problem of how you can integrate these two requirements, that something should at least approximate Newton's law, and yet work with at maximum light speed. And the result was his theory of curved space-time, or general relativity. And I just threw up Einstein's equations here, mostly because they have a kind of elvish rune-like look to them. So I love it purely from the artistic point of view. I'm not asking you to read them. But we can ask, what is this curved space-time? And we should start simply by just asking, what is curved space? And so this is something you can do at home. You can take a basketball and just choose 3 points, A, B, and C, and draw a triangle on the surface of the basketball, in the sense that you draw the shortest path from A to B and the shortest path on the basketball from B to C and C to A. And so if you take a protractor and you actually measure these angles at A and B and C, and you add up and you check with your usual sense that A plus B plus C should be 180 degrees, you will quickly see that it's not true. And of course, you'll tell yourself, I know why it's not true, because I drew it on a basketball instead of a flat piece of paper, right? And that would be true. That's because the basketball, as a two-dimensional, the surface of the basketball is a two-dimensional curved space. So we all have an intuition for that. But now you can ask, what would happen if we drop the constraint of being on this curved two-dimensional surface, and we just do it in three-dimensional space? And so you choose 3 points, A, B, and C, here, A, B, and C, right, in three-dimensional space, and we try to draw the straightest line that we can. So, for example, here's A and B, and I'm going to pull really tight. So presumably, I have drawn a straight line in this pink line here. I've drawn a straight line from A to B, and I could draw another one like this and another one like this, and I'd have this little physical triangle. Now, did I do something wrong? No, there it is. One further. Okay, so you could have these angles like this, and you can add them up and check A plus B plus C. But now, there's no curves, anything around. So if you are paying attention in high school, then the answer would have to be 180 degrees. But in fact, that is not true. It's not exactly 180 degrees, okay? If you use Einstein's equations, you will find that in fact, it's in the vicinity of Earth, like on the stage. The sum of these angles is very, 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 very close to 180 degrees, but it's not exactly 180 degrees, which means that our whole instinct and all the Greek geometers and so on have been going on an approximation. These are not sort of logical necessities that it had to be 180 degrees. This is like an experimental approximation, okay? So that's what curved space is. But I really want to turn to curved space-time, okay? Now, curved space, because it turns out this is a bit of an exaggeration, and if you actually do this experiment, you will not have the precision in your protractors to see that it's not 180 degrees. It's not very intuitive. Curved space-time, the effect is bigger because the speed of light is very big, and turns out that we can actually have a human experience of curved space-time. And so I wanted to show you that. Because it involves time, I can't just draw the picture. I have to do a demonstration. So I'm going to, if you do this at home as a grown-up, then you should have a child supervisor. But here it is. So this is curved space-time, okay? It's gravity, of course, right? It's the fact that we don't keep going in a straight line. We curve our way back down, or if you do this, it's a bit of a parabola. So this is curved space-time in your daily life, but I actually want to apply curved space-time to the entire universe, okay? So that's what the cosmologist would do. So on the scale of the entire universe, curved space-time takes the form of space stretching as a function of time, and it's stretching the same way on the larger scales everywhere, okay? So I have again brought what many of you have probably seen, the balloon demonstration of the expanding universe, okay? But I'll make a simple point about it. So I have drawn onto this many little galaxies in these glittering colors, and as the space stretches, of course, it's a two-dimensional space, but that's all I can afford. If as the two-dimensional space stretches, you'll see the little glittering dots, maybe one of them is our galaxy, are getting further and further away, or other galaxies are getting further and further away from our reference galaxy, which is, say, the Milky Way, okay? So we've all seen some sort of demonstration like that before, but if you actually go and do this at home, you'll test for yourself a simple thing, that the nearby galaxies to your reference galaxy, the Milky Way, the nearby galaxies move more slowly than the ones further apart, so that something that's twice as far away is traveling faster as you keep blowing than something which is half that distance, okay? So that theory of the expanding universe that comes out of Einstein's equations as curved space-time, we can test it, and the test is this famous picture from, so this is one of the, of course, we do much better nowadays, but this is like the second run Hubble had at seeing the expansion of the universe. And basically what you see here is plotted is different galaxies with a straight line fit to this, but where this is the velocities of galaxies moving away from the reference galaxy, which was Hubble inside the Milky Way, as a function of their distance from us, okay, as the function of the distance of the galaxies from us, so that it fits this basic observation as you blow up the balloon, that more distant galaxies get further away, have further away to get from you in a fixed amount of time than the galaxies closer to you, okay? So, so in fact, Hubble's first pass at doing this, all his data fit into this tiny little box here. So this is a vast improvement in the span of 2 years since the 1929 data. Okay. Okay, so what happens, we're trying to get back in time, okay? So we see the universe is expanding, literally, that's what the data shows. And Einstein's equations say that makes sense, that's happening. But we really want to go back in time to the early universe, and so we need to run the movie backwards using the laws of physics and so the extrapolation forward, but we now extrapolate back in time. And of course, if you do that, then the kind of evolution of that sort of fibrous structure that came out of Newton's laws, starting from something very uniform, well, you end up going backward in time, you end up de-evolving, right? Devolving the galaxies so that they come apart and become a more uniform thing. And then, since now we have this relativistic effect of the expansion of the universe, now the universe is contracting, and all of the contents of the galaxies are rushing together into a Big Bang. And again, you can do this at home. There, bang. Okay, so all of the stuff is run together, and what do you get? Okay, so when all the galaxies and all the stars and all the people and the atoms are all squashed by the contraction of the universe, when you run backward in time, you end up creating a big, dense cosmic soup. And the soup looks a bit like this. It's got, even the atoms are crushed out of their individual existence, but their contents are there, neutrons and protons and electrons in this big gooey plasma, It is a kind of London fog in the sense that light cannot penetrate it, okay? So photons interacting with this plasma of charged particles, electrons and protons, does not just travel in a straight line and give you a clean way of looking inside it, okay? So this cosmic soup is opaque to light. Now, it would be great with that theory, that extrapolation backward, if we could go and check it. If there was just some way we could go back in time, enter this sort of phase of cosmic soup and just see it, right? And the amazing thing is that we can, okay? And that's because whenever we look, we are always looking back in time because the speed of light is finite. So as an example, here we are on Earth. If we look at the sun, then we are not seeing the sun as it actually is. We are always seeing the sun as it was a few minutes ago, because it takes a few minutes for light to travel from the sun to Earth, okay? Similarly, if we look at a star, which is, say, one of the nearby stars, which is a few light years away, then it means that we don't see the star as it is. We see the star as it was a few years earlier, okay? For all we know, it's disappeared, exploded in that time. Now, what if we were to look at light from very, very far away? 13 billion, 14 billion light years away, so much so that the light coming to us is not telling us about what's going on now, it's telling us about what was happening 14 billion years ago, roughly at the beginning of the universe, okay? The beginning of just soon after the Big Bang. That would be the era of this cosmic soup. So when we look back in time, we get to this era where, so going back in time, there's sort of this green surface that I've drawn, a spherical surface, where we are at the borderline between being in the cosmic soup regime where you are opaque to light, and just being a little bit after that, where atoms have formed into neutral objects, making the universe transparent to light. So from this last surface, we can get light from the cosmic soup coming, taking the age of the universe to get to our eyes, and then we see it. Okay, so it's great. We just have to look back far enough, and we can see this ancient stuff with our own eyes. How do you see it? So the easiest way is if you get one of those TVs that I grew up with, and go to one of the channels. When I grew up, there were 2 channels, and so you just go to any of the other 10 on the dial or whatever, and you would see some sort of static, and most of that is actually, or a substantial fraction of that is actually this so-called cosmic microwave background. Okay, it is this light from the cosmic soup. Of course, we can do better than that nowadays, and so one is you can use a satellite experiment. So here, it's not the very first, but it is, well, you see why I chose this one, but it's NASA's WMap satellite experiment, where it detects this cosmic microwave background coming from this cosmic soup at the 400,000 years after the Big Bang, which is to say very soon after the Big Bang, coming to us in microwave wavelengths, and it detects it coming from all these different directions, and it can tell about the directions, can look at different directions, and see that it is a very, very uniform color of light. Okay, it is extremely isotropic in the sense that all directions look very much the same as any other direction, but not exactly the same. And so if you take what WMap sees, what you get is as a photograph of this surface, right? I'm saying you can literally see the surface as it was that long ago. And so when I was at Hopkins, the principal investigator of the WMap experiment gave a talk and was handing out WMap balloons, and I got one. So this is it. And what it is it's just a model of this cosmic soup surface. But I told you that the color that they're seeing, it's too infrared for your eye to see, but it's very, very uniform, but it's not exactly uniform. And so if you exaggerate the non-uniformities, then you end up with this sort of set of green-like things with some blue light aberrations and some yellowish aberrations and some red and so on. So you can accentuate the differences and you get a map of this surface that separates the cosmic soup from the regime in which atoms were neutralizing the space. Okay, so there it is. That's why I chose that experiment to first show you. So if you take, just like you do with any globe, you can always take the data on the globe and you can flatten it in some way so you can look at it on the screen. And so there it is. This is the WMap data. And basically what the differences show is that it is a very, very uniform picture of the universe in all directions that you look, but not perfectly uniform. There's like roughly one part in 100,000 variations in the colors, and the colors are tracking the density of the cosmic soup in different directions that you look, okay? So this cosmic soup is not a sort of totally vanilla, boring, bland thing, but a structured picture like this from which a lot can be learned. Okay. Good. So we have some part of the answer that you can start. It's what we're seeing with the CMB, the cosmic microwave background, is a set of non-uniformities, which are very, very small, 1 part in 10 to the 5. And basically, there is a beautiful piece of detective work that the cosmologists have done in matching what the CMB sees as the non-uniformities, the snapshot, direct snapshot of the ancient universe, with what we infer by looking at the galaxies and how they must have formed in large-scale structure from the action of Newton's laws. And basically, in both cases, you need some tiny, in the case of this CMB, you're seeing non-uniformities, which are very tiny, and these match, with sufficient detective work, they match the tiny non-uniformities that you need to start with for galaxies to have formed the structures that we see today under the action of Newton's laws. So there's a beautiful agreement between what we see in the photograph of the ancient universe and what we would infer from the action of Newton's laws, okay? Very good. So it's great, but there's still this burning question. We know we can start from a lot of uniformity, but with tiny, tiny non-uniformities, and we can accentuate the non-uniformities to the very non-uniform universe that we live in today under the action of Newton's laws. But how did these tiny, tiny non-uniformities get there in the first place? Okay, let's back up the question even more, okay? And the answers lie in the 2 pillars of modern physics: quantum mechanics and relativity, okay? So I want to sort of summarize where we are with a metaphor. So we can sort of say, here is a ball, I'm seeing it over here, and it seems like it may have come from this hill, but it could have landed over here instead, and so why did it end up here and not over here? Why is this empty and there's a ball over here? And yet the laws of nature are so even-handed, how could they possibly have chosen, okay? So that's sort of the starting point. And one can ask a deeper question, you know, who even brought the ball, right? But now we see how gravity works. If there was even a slight imbalance earlier, even though the laws of nature are very even-handed, but we started with a slight imbalance, then indeed, with the effect of gravity, it accentuates the difference. Okay, so I've just summarized everything I just told you in this simple cartoon, okay? But the problem, just to remind you, is philosophical, right? But if I balanced it exactly at the top of the hill and the laws of nature are perfectly even-handed, why here and not here? Okay, it's perfectly balanced. Now, if like me, you have, say, two children who both want to sit in the front seat, passenger seat of the car when you're going for a long drive, and they say, you know, I want to, no, I want to, and you love them both equally, or you pretend to, then they're not watching. Then what are you supposed to say? There's only one fair thing to do, right? You have to toss a coin, right? Now, if you want to do that at the level of the fundamental laws of physics tossing a coin, you see, actually a coin is not even a good enough metaphor, because if I really throw a coin with exactly a certain angular momentum, and there's a certain air resistance and so on, if a robot just watched it very carefully and performed the right calculations, it would probably determine exactly where the coin would land. It's only that we're too stupid and too slow to see it, right? But in that sense, a standard coin of your imagination is not even really that random, right? Your children would still complain. You threw it a little bit like this. So for this in principle question, you must have in principle chance. You must have a coin that's truly not pretending to be random, but truly random, okay? So it's just as well that one of the laws of nature, overarching laws of nature, is quantum mechanics, and it's inherently probabilistic. And this was sort of litigated out in the early years of relativity, that if the laws of quantum mechanics were not inherently probabilistic, it would violate the fact that light was the fastest speed. It would violate the tenets of relativity, which in themselves are the only saving feature of causality. That is to say that the cause precedes the effect. Okay, so the whole logical structure of physics depends, as we understand it currently, on quantum mechanics being inherently quantum mechanical. And as a result, it can break all ties, and it does. So if you really, in a quantum mechanics calculation, if you really put the ball at the top of this perfectly symmetric hill, it'll fall one way or the other. 50-50 odds, so it's a symmetric probability distribution, but something will happen, okay? It won't just sit there forever. Okay. Now, you are probably aware that quantum mechanics developed trying to understand atomic structure, and it's basically a big deal when you get down to microscopic scales. So it's surprising to say that it has anything to do with the large-scale structure of the universe, except that if we have a very rapid expansion, space-time expansion, where the universe expands, it is possible for these sort of microscopic quantum mechanical effects, for their effects to be stretched out into macroscopic effects. Okay, so that's exciting. So let's see how that works. So this is the real magic, is this magic incantation of relativity, E equals mc squared, and this is what it means, okay? Of course, I'm sure at home you must have waved your hand and said E equals mc squared and tried to make something appear, and probably many of you have been disappointed. But I'm here to say that's because you are not trying hard enough, okay? So now let me explain. Okay, this is what it means. It means that energy, which is the measure of movement and motion, abracadabra, right, can be traded for something. You can make something out of nothing by just putting in energy, okay? But the c squared, where c is the speed of light, that's the exchange rate, okay? So if you want to use energy to create a tiny amount of something new, you really have to wave your hands a lot. You have to put in a lot of energy to get even a little bit of this new stuff. And that's what I mean. You're just not trying hard enough. But we can go the other direction pretty easily. The exchange rate works in our favor. If you give up even a little bit of, if you destroy even a little bit of mass, you get a ton of energy. And so you're all familiar with this direction. The nuclear energy that fuels the sun, fusion, does exactly that. It turns small changes in the amount of mass of atoms into energy. Nuclear power plants use nuclear fission to do the same thing. Effectively, they are changing the amount of mass of the initial and final states. and turning it into energy, movement, okay? But actually, it's interesting to go in the other direction. This question of who brought the ball makes us think about the other direction where you want to create something. So here, the particle physicists really are doing the magic incantation, and they're trying really hard. And so it works like this. So here, for example, the Large Hadron Collider, deep underground across the Franco-Swiss border, they are accelerating protons to nearly the speed of light and then colliding them. So that's super energetic on the scale of particles. And using those collisions, they are using the magic of this formula, E equals mc squared. So here is a picture of one of the detectors, the CMS detector, where one is seeing these collisions along this axis of this barrel that you're seeing up there, where these collisions are occurring and they are producing new particles that are not inside the proton. They're being created by magic. Okay, this is magic, and that's it. So they're creating things like exotic as the Higgs boson, which is not sitting inside a proton. It's being created by the energy. Or top quarks, which are not there inside the proton. Okay, so they're just creating new stuff, antimatter and so on, in these collisions, and then they have detectors surrounding these collision points to study what comes out. Okay, but I want to talk about where the cosmic soup came from. Who brought the ball, right? So there, if you don't start with the answer, if you don't say, well, somehow the ball showed up, if you say, I started with nothing, then you can ask, so sorry, I got ahead of myself. You can ask, what's moving? If there's nothing around and you want to run E equals mc squared, if there's nothing moving, then how are you supposed to have the left-hand side of E equals mc squared in order to create the matter, the M? Okay, how are you going to do that when there's nothing around? It sounds a bit like, again, a Zen koan or something, but indeed, the space-time expansion itself is a kind of motion which has a kind of energy to it. We usually call that energy the Hubble scale. And this energy of just the expanding empty space is able, by E equals mc squared, to create the particles of this cosmic soup. And so getting back to our question of both creating the particles, but also understanding this question of non-uniformities, we can see a kind of plot taking place, okay? So let's look at that. So the first thing we need is a lot of space-time expansion, okay? We need a lot of energy. And so there is the theory of the growth spurt of the universe, which is called cosmic inflation. And it posits that there is an era of very rapid expansion of the universe very early in its history. In a sense, this expansion is sort of before the bang, as many people would define it, where by bang I mean when all the stuff, all the matter is there all of a sudden, okay? So we can talk about a universe which is in some sense pretty empty, but it's expanding like crazy, okay? And we can see a kind of flow chart for how you make something out of starting with nothing, okay? So first thing you do is you expand like crazy, okay? And whatever happens to be there, there's a few little crumbs lying around, they quickly get diluted away from each other, and so any typical place you look, it's pretty empty, okay? And then E equals mc squared. You've got lots of expansion, you've got lots of movement. The movement is just space expanding. But it's a creative force. So it can create matter and radiation, okay? So that's magic number one. And quantum mechanics acts, so the matter and radiation are created in some randomized way here and there, okay? So it's not perfectly uniform. And then this flow chart keeps going back, cycling back. But the trouble is, this keeps going in a cycle, but that cycle says that then, wait, whatever you created gets expanded away again. It gets diluted so much so that the typical place is pretty empty. So you lose whatever you had created, but you go through the cycle again, and then if you keep going doing this, you keep losing whatever you were gaining, and it doesn't seem like a healthy place to stop, to keep going. So of course, we have to assume something makes it stop. Okay, this growth spurt has to stop. And when it stops, that's the bang, because the stuff that you created, you don't have to go through a cycle of diluting it away super rapidly. It's a bit like if you have a bedroom which you typically end up making a mess of, and then you keep tidying up, then it stays pretty empty, it stays pretty clean. But if you keep putting stuff in it, and you don't ever clean up, then it quickly piles up, okay? So it gets dense, and that's what we mean when we talk about the bang. It's the point at which all the remnants that we have been creating, you get to keep it, okay? It's not all diluted away, okay? So somehow the flow chart has to be that you go through this cycle. Let me see. Okay, I may have lost my pointer, but I will use my hands to gesticulate. So we go through this flow chart, create, expand, and yes, I used up all the energy. But it has to end, okay? And oh, that's you now. Yeah. So I can go back. No, I go the other way. There. Okay. So I have to say this thing that the universe is doing one thing, which is expanding really fast, and creating and expanding and creating and expanding, and then decides, nope, I'm stopping. That means that there has to be this kind of cosmic clock that says, time's up, okay, bang, universe awake, okay, or the modern universe should awake from this period of sort of thinking about creating matter, creating it, but getting rid of it, creating, getting rid of it, but then suddenly you stop. That's the awakening moment for the post-Big Bang era. And there has to be a kind of clock mechanism that tells it when to switch. We have theories of this clock mechanism. We have a number of them. I work on things like this. Many other people have worked on things like this for the last 30 years. But just to say where the data is, we do not have such a good understanding of the data that we see that we can understand what the mechanism is in detail. So we don't know. It's an outstanding question to understand what is the clock mechanism that switches the mode in which the universe evolves. However, this plot line, given such a clock, solves one of our problems, which is the quantum mechanical production of particles gives us non-uniformities. And so in this kind of simple plot, we end up with quantum mechanical breaking of the ties, so that the non-uniformities that we need to start with come from some mechanism such as this. Now, if you wanted to test this, this seems like a just so story. Maybe 10 other stories could be told about how the universe began. So you'd like to test it. And but first you'd have to know what would the universe look like if this was the plot. Then I can compare it with the data and we can check. We should first, and the answer is it's going to be some sort of a fractal-like universe, and let me explain why. First, I want to shut off quantum mechanics. So instead of having expand, create, throw the dice for where you create, return, we're just going to expand, create on a certain scale, and expand, create on a certain scale, the same scale, and just repeat that. So we're dropping the quantum mechanics. We're dropping the probabilistic aspect of it, okay? So here I have create, just this is, now I'm speaking metaphorically. Thank you. Good. So here I've created a triangle, and I'm always going to be creating on the same length scale that you're seeing there. I'm guessing I just use, this does not advance anything. Okay, good, got it, that's fine. Okay, so what's that? The pointer works. That's great. Yeah. So here I'm expanding. There, it got expanded. Now I'm going to create again on the same scale that I created originally. And now I'm going to expand again. And then I'm going to create on the same scale and expand again. Oops. And we keep going. And you see we get what we would call a kind of fractal-like structure, by which is meant that little patches of the design that you're seeing here, like the big rectangle, look self-similar, if you just change the scale, to smaller patches of this design, like the smaller rectangle, okay? So this fractal-like self-similarity is what you would expect if you only had the create, grow mode. And you would end up with an incredibly regular looking universe. Be sort of beautiful to look at, but it would be too perfect to live in. Okay, it's monstrous perfection. Just doesn't allow us to live. That's where we have to now add the quantum mechanics. So now let's go with quantum mechanics. You create, expand, but now you're throwing a coin whether to create or not. So you don't do that last little bit there. So it's a little irregular, okay? Now you expand again and create again, throwing the dice as to whether you actually draw something or not, and you keep going. And you end up with a universe which is kind of fractal-ish, but there's a little element of defects because probability is linked in there. So it's not perfect to look at. And you end up with a universe which has interesting structures on various length scales. And metaphorically speaking, one of those little structures is you. Okay, so this is the kind of fractal universe with quantum mechanics. Now, that's the metaphor, and you can now look at the data again. So here's a more updated picture of the cosmic microwave background. And in fact, what we see in the cosmic microwave background, that structure of non-uniformities that we're seeing, actually has a kind of fractal-like structure to it. That is, with a certain slightly processed view of this, smaller patches of this look self-similar to larger patches of this. Not identical, because there's an element of chance that's woven into creating this. So it's kind of like a statistical fractal or a probabilistic fractal, okay? And this, given that, you might say, well, let me study this fractal. This fractal pattern holds the key to how the machinery of growth and quantum mechanics played out, you know, before the bang. And so cosmologists and particle physicists do that. They study the statistics of the Planck satellite data, and they will have more ambitious measurements in the future. And these are being decoded, okay? And I'll give you an example of what I mean by decoded later, because it'll touch on my research. But basically, already the Planck data, the most recent Planck data from 2018, is very constraining of different options for the cosmic clock mechanism. Doesn't settle exactly what it is, but it at least disfavors some theories of what this cosmic clock mechanism is. It is very sensitive to exotic contents of the cosmic soup, such as dark matter, or even more exotic contents like dark energy. And it's sensitive, and to understand the pattern that we see here statistically, we have to put into it the ancient evolution of the cosmic soup itself and the laws of nature there, okay? So all of these things are buried here, and you might say, I don't see very much with the naked eye, and I'll try to give you an example of what that would look like to decode this in a bit. But this is a lot of what modern cosmology has been about. But I want to say that this cosmic soup might still look, you know, if you look at that, you might say, it's better than if it was totally the same color everywhere, but it's not. It doesn't look that exciting yet. But I want to say that the cosmic soup can undergo other things that are familiar from your regular soup, and one of them is phase transitions. Okay, so as the universe expands, it also cools. Okay, so it's a lot cooler today in the universe than it was at the era of this cosmic soup. And as the universe expands and cools, you can go through phase transitions, which are relativistic analogs of the steam-water phase transition. When you heat up, you boil a pot of water and it turns to steam. You will also form bubbles in the cosmic soup. And these bubbles can collide and they can stir the rest of the cosmic soup. And it's not like your tin pot cosmic regular soups in the restaurant. These are on cosmic scales. I mean, their violence is much greater than bubbles going blip blip in your soup at home. So they reverberate. They give rise to big things. They're like they trigger little earthquakes. The earthquakes of the universe are gravitational waves. They're literally waves of space-time itself, okay? So as a result, we can look to see this. We can try and look for gravitational waves. As you may know, gravitational waves have been seen now to arise from colliding localized astrophysical impacts like two black holes colliding or neutron stars colliding, and we get gravitational waves just from that direction where that happened. But this would be gravitational waves from the entire universe far away from the moment of this phase transition. So let me draw a picture. We would get these kind of wrinkles in space-time where we're sitting here and now we're going back to an era even earlier than the cosmic soup regime, where the earlier regime of the cosmic soup had this kind of a phase transition, okay? And in that era, gravitational waves, not electromagnetic waves, not light, like in the CMB, but gravitational waves, wrinkles in space-time, reach us. For example, they could be detected by this proposed gravitational wave detector, LISA. One of the great advantages, even if you're caught in the infamous London fog of a century ago, you can't see very far, but if a wave of earthquake comes at you, you'll feel it, okay? So these gravitational waves can cut through the opaqueness to light of the cosmic soup, and they can let us see earlier, further back in time than even the cosmic microwave background. And the details of what they show us can tell us about this kind of phase transition, the physics of this phase transition. My own work with a collaboration at UMD, Maryland, we call ourselves the GHOST collaboration for obvious reasons. What we pointed out is that the gravitational wave background you get from all directions can also be non-uniform. So that direction could be different from that direction. And you would get a kind of another map analogous to that, but now in gravitational waves. And it has to be not perfectly uniform. And you might say, well, that just gives us a second copy of something that must look exactly like that. But no, we showed that, in fact, different quantum mechanical processes that lead to these non-uniformities in the cosmic microwave background, there can be different quantum processes that lead to a different looking map when you look at it in gravitational waves, okay? So that it would give you a kind of complementary view of the physics of inflation when these quantum effects were amplified. So I just want to turn to the particle physics very briefly here. So when I was a teenager, I guess, I was very interested in reading all the mythologies of the ancient cultures. I read Indian mythology and Norse mythology and Greek mythology, basically about the ancient gods and how the universe was made. And the ancient gods were always somehow the forces of nature. And they all had a vaguely incestuous relation, family tree, right? So think of my surprise when I find that, in fact, that's exactly the universe we live in. The forces of nature appear to have, here are the four forces of nature, but they appear to have a family relationship where there was some one force that in the course of time always goes down in family trees, started splitting off into separate forces that split off and further and further and further, and you ended up where we are now. This is as much as we can sort of see. There may be other forces, there may be other family trees of forces which we are blind to, but I'm not going into that. And in fact, since as time evolves, you cool in temperature, so temperature goes up this way, the temperature of the universe. So as temperature changes, these are the junctures, these are prime candidates for where the kind of phase transitions could occur that I've been talking about, okay? So I just have to say a word about the structure of particle physics. And it's a kind of archaeology where you walk into a room just to understand what I mean by the birth of these forces. How does that happen, okay? So if you walk into a new building and you see on the floor a whole bunch of fragments of what looks like some pottery or something like that, that's a bit how the particle physicist opens their eyes in this universe and looks around at the laws of nature. The laws of nature are described mathematically, and the components that we see that describe the four forces and all the particles that feel the forces, they have a feel of something that looks like this. They are weird in shape, and there are discrete components, okay, which really are sitting in some mathematics of group theory. But there is some strange, discrete set of shapes that are puzzling in some abstract way, okay? However, the job of the archaeologist, somehow you can piece them together. And it appears that when you take the laws of nature that we just see, you can piece them together mathematically in a jigsaw puzzle, and they fit together in these beautiful unified theories, okay? And so when you see that you can, in your mind's eye, piece them together, a bunch of pottery on the floor, and you can piece it together into something that looks that beautiful, as a detective, it seems plausible to say it must have actually looked like that once upon a time, and it just got broken, right? You wouldn't just see that mess, notice that they fit together, and say, you know, must have just been lying like that the whole time. You're right. This is just too perfect to not say that that's the way it was once upon a time, okay? And of course, what your eye sees is that this elegant theory has these very symmetric forms. And in fact, the electroweak force in your mind's eye, when you see the unified theory of electromagnetism and the weak nuclear interactions, has some symmetry associated with it. And grand unified symmetry is even more beautiful because it's even more beautiful, more symmetric. Now, these symmetries are not symmetries of space. They're not the symmetries of this glass, which is something that's sitting in ordinary space. These are abstract symmetries in abstract spaces associated with the force laws. They are what are called internal spaces. Now, originally in relativity, these internal spaces were related to extra dimensions of space-time that the eye doesn't see. They may still be related to extra dimensions, but I will not talk about that for lack of time. Really, the burning question is, who broke the vase, okay? And just to say, this is the significance of a Higgs boson. The Higgs boson is a hammer for breaking these highly symmetric unified theories into the shards that we see today. Okay? That's what the significance of a Higgs boson particle is. It's its job to do the breaking. So we end up here with the Large Hadron Collider. If you want to check that theory that somebody broke the vase, and I think I'm going to call it the Higgs boson, but I'd like to check what it is, you need to recreate the violence of the original act. Okay? So you need to have a collider to reproduce that level of violence. That's what the Large Hadron Collider does. In energy, it has the energy to sort of recreate both the hammer, creates it out of E equals mc squared, and the way it acts on everybody else to break electroweak unification into electromagnetism and weak nuclear force. And so this is what is being replayed and studied very nicely at the Large Hadron Collider. But to get at the grand unified force, we are orders of magnitude beyond anything. This is not a very linear scale. We're orders of magnitude beyond anything that the Large Hadron Collider could do, or any collider that we can easily envision on Earth could do. Okay, so it looks like that's out of reach. I should also say that these gravity wave detectors, like LISA, the proposed next generation of gravity wave detectors, they would also have, this is not quite right to plot them in energy, but they would have the wavelengths that they're sensitive to would be sensitive to phase transitions in this kind of physics at this kind of energy or temperature. That's what they'd be sensitive to. And again, it's hard to get up to the grand unified force scale. Fortunately, there is another way of getting a lot of violence. Just use space-time expansion itself. During the period of inflation, the expansion of space is so rapid that it gives a kind of E equals mc squared that can create particles that are so heavy that they are not reachable by ordinary collider methods, okay? Terrestrial colliders. And in order to use this, in order to use the universe itself, the early universe, as the collider, right? The energy of expansion, to harness it and have the precision to see the results, we're going to have to go beyond even the Planck CMB data to these kind of three-dimensional maps of the universe, not two-dimensional like the sphere that I am showing you there, that balloon, but three-dimensional maps of the universe in so-called 21 centimeter cosmology, or mapping the galaxies, which of course form a three-dimensional picture, okay? So that's what is there in the future. What I proposed with my student Shobhik Kumar, who's in the audience, is that there is a plot, there's a way in which we can use cosmological collider physics, which is space-time expansion during inflation, as a probe of even this grand unified symmetry breaking, okay, the breakdown of it. And just to give you in 2 slides how that would work, because I haven't given you a concrete example of what do I mean by the statistics of this, okay? So I really have to use these three-dimensional maps. That's what we'll need. I don't happen to have one of these three-dimensional maps of the universe because it's hard to put here, and secondly, the ones we need haven't been done. So I'm just going to use this two-dimensional map and give you the flavor of what do you mean by the statistic? What are you going to find in this crazy pattern here that looks so random? So here's just a kind of a schematic of what I mean, okay? So draw lots and lots of similar triangles. So here, these are all meant to have the same shape, but they have different orientations and different sizes, but they have the same shape. Now, at each corner, there is some color of the CMB light, right? It's all exaggerated here, but there's a little blue there, and there's a little yellow there, and so on. So you take the wavelength of the CMB light. I should really do this in a three-dimensional map, not a two-dimensional map. You take the colors, or the wavelengths, and you multiply them together. And you do this for lots and lots of triangles with this particular shape, but different sizes, different orientations. And you take the average on this whole thing, okay? Some grand average of that. And you compare how that changes as you change this sort of isosceles triangle, as you change the ratio of the long side to the short side. Okay, so let's imagine doing that. At cartoon level, you would get something like this. So here is the average product of the corner wavelengths in all these triangles in the sky. And here I'm plotting the ratio of the sides of the triangle. So the shape of the triangle and the product of colors at its corners. And if you do that, and there really was this unification, grand unification, you would see things like this, okay? They would be waves, okay? They would be these waves, and these waves are waves of the unified force field that is long extinct. It's gone. But we're looking so far back in time that the dinosaur can be, a dinosaur that's seen on another planet 300 million years ago, we can see it today if that planet is 300 million light years away, right? So that's the principle of this thing. But the expansion create thing has scrambled the pattern so much that we have to go through this funny procedure for it to come back out in a way that we can recognize. Okay? Very good. So that is where I sort of want to stop. Just a few points in conclusion. So precision cosmology is leading us to understand these very first moments of creation and answering these tough philosophical questions that are associated with it. Quantum mechanics and relativity they really are magic. Okay, there's nothing else to call them. If you imagine a magical world, then you would get used to it. That's the problem. If you were living in it, but occasionally you have to stop and realize that's the world we're living in. And there's a huge future for these two fields, especially at their nexus. Many, many rich, ambitious, interlocking experiments have been proposed and will likely get done, and there are many theoretical structures that are surrounding them to make sense of them coming up in the decades to come. So stay tuned.
So we have time for some questions. And as many of you know, there is a procedure for questions. And the procedure is that there are people with microphones that have little red, green, or blue foam on them. And I'll call on you by the color. When the microphone comes to you and you're called on, please stand, tell us your name, tell us if you're a member, and ask a question. Save the dialogue for the social hour. So, hands up. I'll start with Carl in the front with the blue microphone, and then we'll go to the red microphone. And speak up, Carl. Put it to your mouth.
Well, two questions. One is that that three-dimensional map that you want to make is only looking at one field, if I understand it. That's the electromagnetic field. But we know there are many fields in the universe. So would that bias your conclusion? So that's number one. And number two, throughout the talk, you seem to be struggling between the force of gravity and the idea that space-time, which maybe that space-time is really not a force, it's a different entity. And as far as I have all the reading I've read, it says there's no granularity that they can detect in it, which you might expect if it were a quantum-like effect. So those are my two questions.
Okay, so let me see, I'll probably go in reverse order. So conventionally, pre-relativity, we did sort of view the forces of nature as forces, that is something that was, in the conventional sense, moving things and accelerating them. And now we say, yes, no, that's just the dynamics of space-time, okay? But the same thing has happened to all the other forces. So the electromagnetic force and so on, we now view in this kind of geometric terms. It's a subtler form of geometry than space-time curvature itself, but all the forces have this kind of, being robbed of the sort of forceness of them. They are all weird kinds of geometry. And the geometry has this kind of elegant structures like the symmetric vase I was showing. They have a kind of elegance that general relativity itself has. So everybody's drawing general relativity rather than saying that they're that different. The quantum structure of general relativity seems to me, almost inevitably got to be there. We don't see the granularity of gravitational waves the way we see granularity of electromagnetic waves in photons, where we can see individual photons. We do not see that yet in general relativity. We understand why we don't see it, because we need a stronger coupling to gravity. Gravity seems like a very strong force. It dominates our life. It's the first force that any caveman would have been aware of. But on a per particle basis, it is orders of magnitude very weak. And that weakness makes it hard to trigger its quantum mechanical granularity. So that's, now, the first part I've already forgotten of your question. I think that was the second half of your question. But I'm not sure whether I got to the first part.
The first part was, well, it was the fact that you're only looking at one.
Oh, yeah. So the idea of looking, so whether it's a three-dimensional map or the three-dimensional maps that we're looking forward to, or even the two-dimensional map of the CMB, they were all electromagnetic. I don't know what we should call this. This is not electromagnetic. This is looking at galaxies and dark matter distributions. So it's already a little bit different. But at least the galaxies are very in sync with electromagnetism. We are all creatures of electromagnetism. So in fact, that was why I was advertising, even at the level of two-dimensional maps, I was advertising this new way of looking in gravitational waves, because it really can spot things that you would have been blind to if you only had an electromagnetic map. Now, do I have a three-dimensional version of this trick? We are looking, some of us at UMD, we're playing with the kind of theories that could be there to see whether it is conceivable that there could be a three-dimensional map that doesn't use electromagnetism. Maybe doesn't necessarily use gravitational waves, but may use something else. We haven't found it yet, but 2 years ago we hadn't found this either. So we'll see. But you do the best you can.
Thank you.
Red microphone.
Hi, Kirby Runyon, and I am a member. Very enjoyable talk, thank you. I'm curious, to enable the kind of precise cosmological observations you'd need, what kind of future space telescopes or spacecraft missions and measurements would you like to see fly?
So we do have, so there's sort of two questions that I raised. One was, for example, better understanding this clock mechanism by which the inflation era of very rapid expansion, accelerating expansion of the universe, gave way to a slower, more sedate expansion post-Big Bang, okay? So that's one of the big questions in cosmology to understand it. That will require, it will require, I think, some deep theoretical developments to try and understand how to place your bets. But it will also require just a more precise measurements of the CMB, which are coming. So there are new CMB probes that we'll see with greater precision, just as Planck has improved on the past. One of the critical measurements that we expect, which we already have constraints coming in on, just from the latest Planck data, is the measurements of, so during inflation, one of the kinds of quantum mechanical particle productions that can take place are gravitons, are gravitational waves, if you like. So these can also be produced by E equals mc squared, okay? And those gravitational waves produced during inflation would not come to our eye as gravitational waves, not like this. Okay, so they're produced as gravitational waves, but instead what they do is they impact the cosmic soup that then sends us the CMB, okay? So we now know that that kind of gravitational wave can be seen by looking at a particular feature of the polarized CMB. And I think you're going to have, in a few more of your talks, maybe 6 more or something, you're going to have a speaker on the BICEP experiment, which was attempting to see these gravitational waves, but ended up not seeing gravitational waves.
Not yet.
Not yet. But the Planck satellite has put constraints. So looking at the CMB, has put constraints on the strength of those gravitational waves. One of the things that tells us the rate at which we see gravitational waves, or see it in the future, will tell us what is that expansion scale. So I said that this creative force during inflation is the expansion rate of the universe itself. Well, that's a number. That's some amount of acceleration, some amount of energy, the so-called Hubble parameter of inflation. We would like to measure that. For example, if we are attempting to use this proposal right here, if we're trying to, say, see grand unified physics, that requires a certain level of, that requires a certain amount of energy in inflation to be able to see that. do we have that amount of energy during inflation? That would be measured by seeing the strength of gravitational wave production. So getting to see that in improvements of CMB measurements would be one of the big holy grails. Because if you can see if you have a detectable amount of the gravitational wave signal in the CMB, that would imply that you are operating during inflation at energies very close to this grand unified scale. Okay, so there's some excitement. There's a proximate target right there. So that's another one. Then there's this three-dimensional maps. Okay, so we will have these improvements in maps of the galaxies and the structure of matter that we can see, which will give us, with high precision, will give us a kind of big data set for these three-dimensional little isosceles triangles I was showing you in exercises like that. But also this 21 centimeter cosmology, which is even more doable. It's more in the future, and it would have to be space-based. And but that's it has already begun. 21 centimeter cosmology has already begun, but going out to very large distances in the universe is still some time away. That would be again another feat of experimental cosmology, where we could learn maybe the maximum that we could milk in electromagnetic radiation from the Big Bang.
Yellow microphone, and then the blue, and somebody must have the red. So yellow, blue, red.
Hi, so great talk. Niraj Trivedi, not a member. So I was really fascinated by the three-dimensional cube that you had with, all the soup, and then over time it had almost these, I kind of looked at them as highways where all these gravitational maps were there. And so it struck me that, if you have these sort of gravitational highways, so to speak, how does one portion of the highway affect another, especially if there's, some kind of disturbance or something? Can you change this highway over time, and how do you track that?
So the kind of, so I wasn't calling it highway so much as I was calling it this sort of fibrous look of the universe today. And I would say the word highway suggests that there is some fast passage if you just stayed on the fibers of this fibrous universe that we seem to live in, that somehow you'd have a fast track to go from place to place. And that's just not true. So that aspect of the word highway should not be considered. But there is this sort of fibrous feel to it on the largest scales. When you're looking at the universe, you see this kind of fibrous feel to it. Now, the fibers do affect each other, again, through Newton's laws, in the sense that that's actually that's creating the fibers, that there is some sort of an instability starting from a fairly uniform but not perfectly uniform initial state, that there seems to be, as we see by running Newton's laws in the simulations, the tendency to form these fibers. I don't think I have a brilliant, there probably is a simple way, but I don't have a brilliant insight into why Newton's laws inevitably seem to lead so typically to this fibrous look. But do the fibers interact gravitationally? Yes, they do. And in fact, that gravitational interaction is partly creating the fibrous look in the first place, but they're not highways.
Okay, before we go to blue, let's take one from the web. Do you have a question there from the chat? So read the question. Oh, yes, you need a mic. Sorry.
So the first question is from Neil, who's not a member, and he wants to know, what are your thoughts on time?
So oddly enough, so look, by the standards of my daily beat, what I've been talking about is actually very practical, but by my standards, okay? This is, like, it relates to data and so on. However, there's something amazing about the data. If you look at what we are actually looking at in the end is, let me just get that, okay. This is a moment in time. This is a snapshot, it's a photograph. Now that's what the universe hands you. All the stories I'm telling about, grow, create, stop, clock goes off, wake up, the universe, all of that is inferred as the simplest way of saying what this pattern is, okay? So there's a pattern here. It looks a little muddy to you, but there really is statistically very sharp patterns in this data. And to make sense of it, we actually, so you walk in the scene and you see a bunch of fossils. They look like bones, this, that, and the other, and you infer that there was a prehistory of dinosaurs walking the earth, et cetera, et cetera. So you see that in your mind already, the only data, if you just stick with the data, it is this one instant, more or less today, where I see the fossil record. And in it, I invoke a kind of time that is there to make sense of it, right? Now, you might say, yeah, that's sort of the usual detective work. We come on the scene, and we see, that's how we do archaeology, that's how we do paleontology, whatever it is, and that's what we're doing here. However, there's something very funny. There is a sense that this kind of moment in time where there's space, that's what we're seeing, space with some interesting structure, has an almost autonomous existence. And that time is really emergent. So we see in a pragmatic level that time is emergent. That's a fancy way of saying, I saw a snapshot, and from looking at the facts, as a detective, I was trying to figure out how that snapshot came to be. So that seems like, yeah, okay, time is emergent in that sense, but don't make such a mystical thing out of it. However, I'm saying something stronger. The nature of this snapshot and things like it that come out of relativity seem to be pointing to a possibility that time is emergent. That in some sense, this is the reality. This is not a snapshot of a reality where time played all the time and then we just got a snapshot of it. That in some sense, the snapshot is everything. And our inference that there is time is a kind of imaginative inference. Now, the reason I say that is partly because in general relativity, there is a sense in which time is a kind of a fiction. It's not a physical reality, but it's sort of the way you look at, there's a timeless state, and the way you look at it gives you sort of the illusion of time at different stages. But the truth is sort of, the invariant truth is a kind of timeless snapshot. So there's already that kind of thing. But there's also an analogy between the physics of the accelerating and expanding universe during inflation and other theories that Juan Maldacena spoke about here some lectures ago, where we see how space, one direction of space can actually be emergent, okay? So it's not really there, but it's a bloody good illusion, okay? So similarly, if you go this one extra step, there is a direction of speculation with some mathematical backup that time itself may be emergent. That makes it very difficult for physicists who are always trying to understand, like our baseline question is, I tell you what happened now, you tell me what happens later. That's physics. So if you take away time as itself being fundamental, that pulls the rug out from under us. But there's enough clues here that may be driving us to doing that. Very much like in the birth of quantum mechanics, the separation between particles and waves was lost. And we had to unify the two with a deeper understanding, which words at the time could not even express. Here, the sense that, no, there's no time, or time is emergent, almost seems beyond our ability to express. But there are hints that that's the truth. So those are my thoughts on time.
Okay, awesome. And then I want to say this is pronounced Merle Patterson wants to know, could antimatter exist beyond the CMB horizon?
Yes, absolutely, because in fact, in the era in which the CMB switched from being opaque to light to being transparent to light, which is the regime from which the light that we get from the CMB emerged, we largely don't have a lot of antimatter. We have electrons and protons, but not lots of positrons and antiprotons. But in fact, if you go even earlier, so you go beyond that CMB, or further out, which is earlier in time, then in fact you end up in a regime where there's lots of antimatter. And in fact, if we just extrapolate our universe further and further back in time, assuming the laws of nature in my family tree, you see that there's almost equal amounts of antimatter and matter. So that you actually come to another of these great mythical stories, which is a perfect balance, almost perfect balance between matter and antimatter in the super early universe. And they are literally in a war of annihilation, okay? There's the good guys, we always call ourselves the good guys, and then there's the bad guys, but they're almost, evil twins. Each one thinks they're the evil twin of the other, or the other is the evil twin of them. And they are in a battle of mutual annihilation. They are just annihilating with each other into energy, or into photons, or something like that. And for some reason, one side wins, and the other is completely annihilated. So most of the antimatter then disappears from the universe. And there's it's almost a draw. So there's only a sliver of ordinary matter left. And that's us, okay? So there's another huge puzzle, which I work on and many people work on, which is the puzzle of how was the matter-antimatter war not a perfect draw? What tipped the balance in our favor? And what experiments can we do to test that story? And that's a fascinating, I was almost thinking of giving that talk here, but I chose this one.
Another time. Yeah. Lou.
Timothy Thomas, I am a member. My question is about your diagram. Maybe you can put it up again, the circular one with the gravity wave detector in the center.
Yeah.
That shows that one.
Yes.
Outside that soupy area is before the Big Bang.
No. Outside this soupy area is an earlier era, which is also post-Big Bang, which is here. So it's more soup. It's more soup, but it's bubbly soup.
And those bubbles, et cetera, and the
there's lots of
gravity
antimatter
waves.
here.
So have these been detected beyond this period?
This
and
is a
why
target.
do you think there's only a bunch of them rather than just one?
A bunch of
Gravity waves.
Because the uniformity of the universe is at least very, very close to true in this earlier era, okay? And so what's happening in this part of the soup is very much what's happening in this part of the soup. So if this soup is violent enough to give us observable gravitational waves from this direction, then it's pretty much the same soup over here.
So it ought to be.
And so we ought to. And in fact, our paper was pointing out that it should not, however, be exactly as good. So there should be some variation in the gravitational wave
Is this
signal.
device in the center to indicate that someday these
these
gravity
are like
waves
satellites.
will be detected?
Sorry, yeah, this is the lease up. This is a proposed, but it's the most likely to be done in the next 10, 20 years. Detector that would be in space-based, using laser interferometry to detect the passage of these very weak wrinkles in space-time. That would be their purpose. Yeah, they would be there. They would be able to detect this, and they would have some sensitivity to the direction in which this is coming from. So we could test whether it really is the same in this direction or this direction.
You're expecting to see a lot of them.
We have to be lucky that there is a phase transition violent enough to do this. So we are opportunists. So when you say the word expect, I say hope.
Red microphone.
Yes, my name is Scott Matthews. I am not a member. It would seem to me that in the early universe, there would be copious amounts of neutrinos being produced. And I'm wondering whether the cosmic soup would be transparent as far as the neutrinos are concerned, and whether you could effectively see beyond this horizon further back in time if you were looking at the neutrinos. And then I have a second real quick question, which is your balloon, your CMB balloon seems to show an axis of symmetry, like an equator,
Yes.
that I don't see in the flat images. Could you comment on that?
Good question. Okay, so starting with that one. So in the actual map of the CMB sphere, there is this big red patch here, or a strip. And that is actually, remember, we're in the middle of this. We're in the middle, right? So what we're actually seeing is the disk of the galaxy, from which we have a non-cosmological, more astrophysical source of microwave radiation. And so it's there, and they have cleverly doctored the picture so that it's not showing in that one. So you have to remove this as a kind of a, we don't call it a background, it's a foreground, because it's even close, the galaxy is even closer to us. So that's been removed. With regard to neutrinos, yeah, they should be passing through they're much more easily through the cosmic soup. And there is the goal of trying to see a neutrino background, and how much we can learn about going back even earlier, just using neutrinos, I am not immediately aware. There may be one of my colleagues here in the audience who knows the answer, but I don't think, we don't discuss it a lot as, it's a good question. I don't know that we discuss it a lot as a way of going in the direction. So there's one aspect that's really problematic with neutrinos. The light travels in a straight line. The neutrinos, they have mass. They are not perfectly massless. So they're not necessarily traveling in a straight line. They can also feel Newtonian effects of pulling and so on. So they're not a very faithful messenger. So in that sense, not as useful.
Blue microphone.
Glenn Chinnery, I am a member. I was wondering at each of these phase transitions where you have a decoupling of the forces, and you sort of give an analogy of it as a condensation, perhaps, of a field out of the universe. If you look at a classical analog like the droplets of vapor being sucked up by a hurricane and hitting the colder atmosphere, and then condensing, and they release their heat of condensation. Does that decoupling also release a analogous heat of vaporization?
Yeah.
And you get additional energy injected into the universe at that time?
They can. So the question of whether during these phase transitions there can be some heat of the phase transition that is released, absolutely, it can happen. And in different theories of each of these bifurcations, you might be able to calculate what that is. But so that can happen in some of, like when we were trying to show the value of this gravitational wave map of the sky, we had to take into account that kind of effect to show, look, interesting things could happen in cosmological history, including that, and we need to take that into account in seeing how you would compare the gravitational map of the sky with the electromagnetic CMB map of the sky. So, yeah.
Have a yellow microphone back there somewhere?
Hi, I'm Townsend Cock. I'm not a member.
Hold it close to your mouth.
Oh, sorry. I'm Townsend Cock. I'm not a member. My question was about the sort of pieces of the grand unified force vase that you were talking about earlier. Could you just maybe like give an example of that and how those pieces are related to group theory, and maybe also how I recently learned that the Poincare group was like somehow had to do with special relativity. Maybe you could talk about that a little bit. I don't know.
So just say the second bit again, would you? Just the part about the special.
The Poincare group, like what does that have to do? Is that a piece of the puzzle of the phase of the grand unified force or something?
So let me start with the first bit, which is, so here's this amazing thing. We say that There's the electromagnetic force, and it has a force carrier, the photon. And there is the weak nuclear force, and it has a force carrier, which is called the W boson. And there are two of them. One is positively charged and one is negatively charged, so there's two of these. And it turns out there's another kind of weak interaction which is less heard about in your high school books, say, which is called a neutral current. Okay, so it's got a force carrier called the Z. So if you look at these different force carriers and you sort of take three linear combinations, out of these four, you sort of choose three of them, but in some linear combination, you find that there's a kind of, you can do a rotation, just like I'm doing a rotation between these three directions, up, forward and sideways, and I can do a rotation. You find that in the space of force carriers, which is a very abstract thing, right? This is the photon, this is the W plus, this is W. In this space, there's a kind, if you look at the interaction strengths, the data, you look at the interaction strengths, there is a kind of rotational symmetry to the data in terms of the interactions, but it's not shared by the masses of particles. So the masses of particles also can be sort of, you can ask in this abstract sense, if I do a rotation, does the body of data on masses of elementary particles, do they respect this kind of rotation symmetry? They don't, okay? And so this, but let's put that aside for a second. The fact that the strength of interactions of many, many, many different processes don't seem to care whether I rotate the weak force carriers with the photon, right? It's bizarre, and that's a rotation. So when I say symmetry group, that's the group of three-dimensional rotations, not three-dimensional rotations in ordinary space, but in this abstract space. That's why I called it internal space. So if you now because the masses don't respect it, if you actually look with the naked eye at processes that they care about interaction strengths and masses at the same time, if you look at the raw data, you won't see with your naked eye this amazing thing that just the interactions by themselves have this symmetry. They won't catch your eye because the masses come into the same processes and screw up the data in a biased way. So that is bizarre. That's the unification that you're seeing. In the grand unified theory, it's also a kind of rotation, okay? But it's not three-dimensional rotations. It's not even the two-dimensional rotational symmetry just to rotate in one direction that this glass has as a symmetry. They are 10-dimensional rotations, okay? That means if you lived in a 10-dimensional space and you allowed yourself every conceivable rotation, then that's the rotations that we're talking about for the grand unified theories. And it's remarkable that there are fragments of the pottery, meaning the stuff that we see today, the particles and forces that we see today, and they seem to fit together once we turn a blind eye to the masses column of the data and only look at interaction strength. They seem to respect that symmetry. 10-dimensional rotations in an abstract internal space, okay, bizarre. Now, the only reason the masses don't respect this, that's the result of the Higgs. The job of the Higgs is, how does it break this very symmetric structure? It screws up the symmetry of all the masses of elementary particles so they do not respect this rotational symmetry, but keeps the interaction strengths symmetric enough that there's a clue for humans to find, right? So, but not to the naked eye. Somebody had to, piece these things out separately to see that there really was a symmetry. So these are really stunning symmetries, 10-dimensional, the rotation group in 10-dimensional space. And, but we're sitting on top of it. As I said, in the early days of relativity, there was some sense that extra dimensions had something to do with this phenomenon, and that the internal space that I'm talking about, which is purely an abstraction, it's the direction of force fields or something, was actually the space of small dimensions that are curled up too small to see. So they were literally internal spaces in the sense that they were just extra dimensional spaces, but instead of going on forever, they were curled up. Nowadays, they may still play a very important role, and a lot of my work is to say what that kind of role would be, but it is not quite as simple as saying that the internal space is the space of these extra dimensions.
Last question, red microphone.
Wow. I have two kind of yes, nos, and then a more open one if you want.
Let's stick to the
when
two
you
yes,
talked
nos.
about the expanding universe, is it
It's like-
safe to, and you talked about it being a consequence of relativity, is that expansion and relativity and curved space-time, is that due to the mass of the stuff that you're creating out of nothing that you described in that cycle? Is that a good way to think of it?
It is definitely because of the stuff in the universe that says that the universe doesn't want to sit still. It could contract, but it could expand. And so we happen to see it expanding. And it is because of the stuff that's there. Whether it was created in the way I said, according to the theory of inflation, or done some other way, it would result in the universe not wanting to sit still.
But it's not external. It's not some external thing causing that curve.
Now, there is another part of the expansion, which is in the modern, it's not played a role in the very ancient days that I was talking about, but in the modern time that we live, another force, which is not to do with the ordinary stuff of the universe, is causing the universe to expand, and that's called dark energy.
Right.
It's well fit by one term in Einstein's equation called the cosmological constant. It's not a stuff in the sense that other things that cause the universe not to sit still are stuff, like you and I are part of the cause of that. So that, we don't know exactly what it is experimentally. We can have a theory that it's a cosmological constant. We don't know exactly what it is, and it is a huge enterprise to try and find out for sure what it is. There are many mysteries surrounding it.
Last question?
Yep. On the Ancestry.com chart,
Yes.
that lowest...
I didn't say Ancestry.com, I said Ancestry.cosmos.
Yep, I wrote Cosmos, but you know what I
Don't sue
meant.
me.
That lowest energy level phase transition,
Yes.
is it wrong to correlate that with the cosmic soup, that transition out of the cosmic soup?
Yes.
Is that the same
It's wrong.
transition?
In other words, that is a even in the resolution of my picture did not even feature. It would have been very far down the picture, where that transition is really where the universe is so hot that, and violent, if you like, that atoms are broken up into protons and electrons separately. And then there's when the universe cools a little more, becomes a little more passive, you form neutral hydrogen atoms. So that's that transition.
Mhm.
And that is well after this bifurcation of the electroweak into electromagnetism and weak nuclear force.
After, meaning it came earlier?
That came earlier.
Got it.
That
Okay,
came way earlier.
super. And I'll save the NEMA question for across the street.
Okay. So, Ron, before you go, we have a small token of thanks for you.
Thank you.
Let's go to the middle of the stage.
Okay.
So first we have a framed copy of the announcement of your talk, signed by all of the members of the General Committee on behalf of all the members of the Society. And we have a copy of the Bulletin, Volume 1, where you can learn about why they call it philosophical
Very good.
and who founded it,
Okay.
and that it was really about science, and one of the main founders was Joseph Henry, so your physicists will know who he was.
Right.
And thank you very much.
Thank you.
Before we go, there are a few housekeeping announcements, and I'd like to bring you up to date on the schedule. As you know, PSW depends on members and sponsors, without which we wouldn't be able to offer these lectures for free. If you're not a member, please consider joining. And if you are a member, please consider paying your dues if you haven't. already. And if you have, please consider giving a bit more, perhaps becoming a sponsor or volunteering to help carry out the Society's activities. If you're not a member, you can apply for membership by going to the PSW website, PSW Science website, and on the home page, hitting the join button. This is really easy. Anybody can do it. And when you do that, you'll pull up this page and you'll have a membership link here. I suggest using this one, not that one. And that will pull up the membership application form, which you must fill out wherever there is a red asterisk. Those fields are required. Just some basic information about you and your interest in science. Nothing more is required. No high IQ, no expectation of winning a Nobel Prize. Just an interest in science. And then pay the dues, submit the form. And you can use a debit card or a credit card to pay dues. You don't have to use PayPal. So don't worry about that. So, upcoming lectures. Oh, I should say, PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code, at least for the time being. Contributions are tax deductible to the extent permitted by law in the IRS. All PSW members in good standing, including new members, can wear the PSW rosette. If you wish to purchase one, they're $15, and you may do so at the rosette table at the back of the room. Please speak to whoever is going to be at the rosette table. The next lecture will be at 8 p.m. here in the Powell Auditorium on Friday, February 22nd. The speaker will be Compton J. Tucker, Senior Scientist in the Earth Sciences Division at NASA Goddard Space Flight Center. He will be speaking on satellites, dinosaurs, Milankovitch cycles, and Cretaceous Earth. Some of you may know, Compton Tucker is very well known for having developed the methods that we use now to interpret vegetation and plant growth and plant death and crop yields and other things using satellite data. So based on a ratio of infrared sensors. The rest of the spring schedule is complete until somebody else decides that maybe they can't do what they promised to do. So our next speaker will be, after Compton, is Ramesh Gopinath of IBM. He'll be speaking about the use of blockchains in commerce. On March 22nd, we're going to hear from Jim Garvin, and some friends of his are going to tell us about Venus. On April 12th, we're back to physics. We're going to hear from Mary Angela Lasanti of Princeton. She's speaking on dark matter, and her lecture is sponsored by PSW member Erica Kane. On April 26th, we have a very interesting talk by a colleague of mine, Kim Janda from the Scripps Research Institute. He is trying to develop vaccines that basically render drugs of abuse not worth abusing. And on April 29th, we have a very special event. Alan Stern and Ron Eckers will be debating whether Pluto is a planet from the standpoint of what is the proper definition of a planet. We're hoping that Ellen Stofan will be the moderator for this discussion, and that will be a lecture or event sponsored by PSW member Gene Shaw. And then finally, our last event of the season will be on May 17th. The 87th Joseph Henry Lecture will be delivered by Back to Physics, Brian Keating. I'm hoping that he will talk about inflation and the beginning of all things. And that lecture will be sponsored by Millen White, Solano, and Brannigan. And with that, note that the social hour ends at 10:30, after which PSW members and guests meet at the Fairfax Hotel Lounge just across Massachusetts Avenue. If you want to join us, please speak with corresponding Secretary Robin Taylor, Membership Director Lloyd Mitchell, or myself during the social hour. Please use the side entrance to exit the building. The side entrance is now known as the side exit. I will now accept a motion for adjournment of the 2,403rd meeting of the Society to the social hour. I have a few motions, seconds. I have many seconds. All those in favor? All those opposed? The meeting is adjourned to the social hour.